rolling disk. We have a disk which is rolling on a flat plane. There is no friction nor sliding. We know the mass of the disk, the radius, and the gravity. We have three angles for the disk, phi, theta, and psi, the Euler angle. The projection C1, C2 for the center of gravity, and the derivative of the Euler angle form the state vector x. In this exercise, we have to find the state equation for this disk. And the first question is to express the Lagrangian, because we use a Lagrangian method in order to find these state equations. The disk is represented here. There is a center C in 3D, and the projection has for coordinate C1 and C2. The state variable for this disk are the degrees of freedom. So it's composed X. We have the degree of freedom. The degree of freedom are C1 and C2, the projection on the horizontal plane. So these three along the z coordinate can be expressed with respect to the other state variables. We have phi, theta, and psi, the Euler angles. We also have the derivative c dot, theta dot, and psi dot, the derivative of the Euler angles. And the other derivative, for instance, for C1 and C2, can be computed analytically from all these state variables. So we don't need to add them. So phi corresponds, it's along x-axis, is the spin angle. So the wheel rotates spin around x. Theta is a stand angle, so it means that when theta equals 0, the disk is vertical. And the heading is the psi angle. So in this situation, the wheel is moving in this direction. So so we can see here that psi is not directly the heading if we consider it as a vehicle, but if I move psi, then I will see that the heading of the wheel will change. The Lagrangian L is a function of q and q dot, where q corresponds to the vector of degrees of freedom. So q is equal to C1 and C2, and phi, theta, and psi. The Lagrangian is the difference between the kinetic energy, which depends on q and q dot, and the potential energy, EP, which depends on q only. So for the kinetic energy, it is equal to half of the rotation vector omega r expressed in the body frame multiplied by I, the inertia matrix in the body frame, multiplied by omega r, plus half m, the norm of c, so the three-dimensional vector, square. Okay. The inertia matrix I is equal, so it's a matrix which is a diagonal, and it is mr2 divided by 2, mr2 divided by 4, and mr2 divided by 4. So it is a diagonal matrix. And the potential energy, so EP, is equal in our situation mg r, the radius of the wheel, multiplied by cosinus theta, the stand angle. Okay. So now, to have an expression of the Lagrangian, I need to express here WR, and for this I will need an expression for R and an expression after I will deduce an expression for omega R. So recall that R is equal to is obtained from the Euler angle by taking the exponential of ck, so k this vector, I and j, multiply by exponential theta g multiplied by exponential phi I up. Okay. So if I obtain with this the Euler matrix, which I recall is given here, so it is a function of phi, theta, and psi, which are here in the vector of the degrees of freedom. So now from this, I recall how to obtain an expression for WR. So I will explain it now. I know that R transpose multiplied by R dot is directly related to omega R, so the rotation vector expressed in the body frame. It is a skew symmetric matrix which is given by this: omega R third coordinate, omega R second coordinate, minus omega R first coordinate, and here it is skew symmetric, so it means here I have omega R 3 minus omega R 2 omega R 1. Okay. So due to this, if I compute R, I have an expression for R. I will have an expression for R dot. I will not do it here, but I have thus an expression for this. If I extract here this coefficient, then I will obtain an expression of omega R, which will be given by something like phi dot minus psi dot sin theta, theta dot cos phi plus psi dot sin phi cos theta, and here minus theta dot sin phi plus psi dot cos theta times cos phi. So I have an expression for omega R. As a consequence, I will have an expression for the Lagrangian. So for this, I will use SimP because I don't want to perform all computation by hand, and it is what I will do now. I take the following Python program where I will use SimP for symbolic computation. I create the symbol I will need in this exercise. So I need t, I need the mass, the gravity, I need some function for the trajectory, c1, c2 for the projection of the center of the wheel, the first derivative, the second derivative that will be used later, the Euler angles, and the first and second derivative. As I explained previously, I have to build the Euler matrix associated with phi, theta, and psi. So there are, I recall this formula. Okay, and the first line corresponds to the exponential on the right, and the last line the exponential on the left, and I multiply the three of them. Then I recall here that I have to compute R transpose R dot here. So this one is computed here. So I use the symbolic differentiation with respect to t, and then I will extract the three components, the three entries of this matrix that will make me the vector omega r, okay, the rotation vector. Then I will print them. So I will show you how it works. The program is given here. I run it. And I will obtain an expression for r and an expression for omega r I have just shown previously. To compute an expression for the Lagrangian, I will use what I have described before. So I will make the difference between the kinetic energy and the potential energy. The kinetic energy which is given here. Okay. The inertia matrix. The potential energy is given here. For the potential energy, I need to compute the coordinates of the three-dimensional vector C. From C1 and C2, which belongs to Q, I should compute the altitude of the center C, given here. And I need to compute its derivative to get the kinetic energy. And then I will use here a function substitutive, will simplify, as we'll see illustrated just after, will replace some function like this by the variables I will need later. Okay. So the Q vector, the vector of degree of freedom, is given here, and its derivative is given here, and the Lagrangian depends on Q and dq. And we'll see that if I use simply for this, it will print me this function for the Lagrangian, which depends on Q and Q dot. I run. And I see here an expression for the Lagrangian. Okay. If I don't put the expression substitutive, like this, if I run it, I will observe that in the expression I obtain something like derivative of phi and so on, and I don't want this. I want to substitute this kind of expression by the variable dd phi, for instance. Question number 2. We first assume that the wheel is on a flat frozen lake, so it can slide in all directions, horizontally and laterally. So what we'll see later, there is no non-autonomous constraints. In this situation, then q dot will correspond to the state vector, and we'll have q here and the derivative, so we have a vector, a state vector of dimension 10. And we can obtain the state equation using the Euler-Lagrange equation, which are given here. So tau corresponds to the external constraint forces. So here in this situation, since everything is frozen, everything is sliding everywhere, I will assume that tau equals 0, and I have to find the expression for this differential equation. I mean, I have to find an expression for q, because if I have q, I will have the differential equation describing the motion of the disk. The Euler-Lagrange equation is given by like this, the derivative with respect to t of the partial derivative of L respect to q dot minus the partial derivative of the Lagrangian with respect to q is equal to the external forces. So we should understand that this is a function of q and q dot. This one also, it's a function of q and q dot, but since I compute the derivative, here all this depends on q, q dot, and q dot dot. So all this I have to compute an expression. It will be q, which will depend on q, q dot, and q dot dot. And here, tau, there is no external force to start, so it will be equal to 0. So just have to find an expression for q. So for this, I will do like this. I compute symbolically, and I will do it later with SimP. So this, we'll see that indeed L, the derivative with respect to q dot, is a function of the degrees of freedom and their derivative. If I make the derivative with respect to t, then I will see that some phi psi dot dot will appear. Then for this one, I will have this expression, and at the end, I obtain an expression for q given here. Okay. We should understand that it is not necessary to do all this computation by hand, and this is why I will use SimP for this. With SimP, I will write this, where I compute the Jacobian of the Lagrangian with respect to q, to have this to have that. Then I differentiate with respect to t, given here. And then, of course, I make the substitution to simplify the expression. And then I will print it. This is written here. I run it. And SimP will return the expression for q given here. Question number 3. So we assume now that we are not anymore on a frozen lake, and no sliding is possible. The disk can only roll. So it means that this point, the contact point, has a speed which is like this, in this direction. So follows. So we have some differential equations which are given here and that we have to prove. So these constraints are said to be non-autonomous because they relate, it's a constraint between q and the q dot. And it is not possible to get rid of 1 degree of freedom to return in a situation where q and q dot are independent. So here they are dependent. So how to prove this? First, we need to understand that the C dot, or C1 dot and C2 dot are linear combination, can only change if the angle are changing. So they are depend linearly on phi dot, theta dot, and psi dot, the derivative of the Euler angles. If the Euler angles are static, then the point C will not move. So it means that I have something like alpha 1, which depends on q of phi dot, plus alpha 2 theta dot, plus alpha 3 psi dot, and this one will be something else, beta 1, which also depends on q, phi dot plus beta 2 theta dot plus beta 3 psi dot. So now I need to find the expression for this, this, and this, and I will see that they are given by this, this, and so on. So how to obtain this? I will consider different situation where all are static except one of the rectangles. So first, only phi is changing, after only theta, and after only psi. So for this, I will generate three situations. In the first one, so I take this one equals 0, this one equals 0, and this one is changing, only phi. So in this case, I can see that the point C is translating, and I will have C dot 1 is equal to R sin psi multiplied by phi dot, and here C dot 2 equal minus R cos psi multiplied by phi dot. Okay, so here only phi dot is is different of 0. Okay. Now I consider this situation where phi dot equals 0, so I'm not spinning anymore. Here the heading is not changing, so only this one is changing, only theta, so it is falling down. Only the stand angle is changing, and we can see that C is moving, and so it will be the case for its projection, which would translate like this. So we can see here that C dot 1 is equal, and C dot 2 will be equal to, so it will be here the cos of theta, so R cos psi, cos theta multiplied by theta dot, and here it will be R sin psi multiplied by cos theta multiplied by theta dot. So we can understand this. Now the last situation is different. So the stand angle does not change, phi does not change also, and only the heading is changing. So we can see here that the contact point is here, and the wheel can turn like this, but the contact point is not changing. Okay, like a coin which is spinning on itself, if you want. So in this situation, I will have C dot 1 equal and C dot 2 equal. So here I will have minus R sin psi sin theta psi dot, and here R cos psi sin theta psi dot. Okay, psi dot. So by superposition, we get the equation to be proved. So which was given here. Okay, so we can see that I have the different situation I have explained before. This one and this one and this one. These constraints are said to be non-holonomic, since they will not allow us to express our system with a states composed of some degrees of freedom q and their derivative. Question number 4. So we assume that we have no friction, no force to thrust or to slow down the disk, so the energy of the disk remains constant. So the only external force that apply to the disk correspond to the reaction forces of the ground on the disk. So we need to use the principle of D'Alembert to compute tau, okay, in the Euler-Lagrange equation in order to get the state equation of the rolling wheel. So what we have to do, we have to prove that tau is a linear combination of two vectors, this vector and this vector, and the coefficient lambda 1, lambda 2 that are named the Lagrange parameters depends also on Q. It is what I have to prove. So for this, I need to take a virtual displacement. So a virtual displacement corresponds to a displacement of Q, the degrees of freedom, which is consistent with a feasible trajectory. Now, I know that all feasible trajectory should satisfy this differential equation. So it means that if I take a virtual displacement delta Q, so the corresponding delta C1, delta phi, and so on, I should satisfy this equation, which is exactly the same as this one, except that I have replaced the time derivative by a displacement. Okay. Now I can see that this equation is linear with respect to the delta Q. So it means that I can write in a vector form like this one, where I have delta Q here, and this coefficient here corresponds to 1, this one corresponds to this one here, delta C1 is here, and this one is here, and so on. Okay, so I have written this equation into this matrix form. Now, the principle of D'Alembert tells me that I always have the corresponding work which is equal to tau transpose times delta Q. So it is the definition of the work. So since it is a small displacement, I will have a small variation of work. But this small variation of work should always be equal to 0. So since it is always the case, it means that tau should be a linear combination of this vector and this vector. Now this vector here, this line vector, corresponds to this column vector here, and this one corresponds to this one. Okay. So due to this, I obtain that tau is a linear combination of this vector and this vector. So this is what I write here. And I obtain this one. So tau depends on Q, okay, and on a two-dimensional parameter, lambda, the Lagrange parameters. Question number 5, I have to give the state equation of the rolling disk. I have already computed Q and an expression for tau. And from the Euler-Lagrange equation, I know that Q of Q dot, this one, is equal to tau, which depends on Q and the Lagrange parameters tau. If I rewrite this equation, I obtain 5 equations given here. Okay, so it means that this one has been on the left hand, and here I have put equal to 0. So I have 5 equations, one here, one here, one here, one here, and one here. So first, I observe that I have 5 equations with 7 variables of interest. It corresponds to lambda, which is equal to lambda 1 and lambda 2, and Q dot dot. So it corresponds to C dot dot 1, C dot dot 2, and also phi dot dot theta dot dot and psi dot dot. Well, so we observe that in this equation, as it was the case previously also, we observe that all variables in Q dot dot occur linearly, and also for the Lagrange parameter. So this one, this one, this one, and so on, they appear linearly. Okay. So now if I take also the previous equation, like this one, yes, this one, then I have, so it was, I had shown before, it was not exactly this one because it was a derivative, so I had 1 of q, a of q, so this corresponds to a, times q dot, so I replace here the delta q by q dot, it should be equal to 0. So this one, I will call it, for simplicity, a small a of q dot. Okay. And I need an equation, I need to add 2 equations in order to have 7 variables for 7 equations. So I need 2 more equations. This is why I need to differentiate this one to make q dot dot appear. This is why I differentiate this one, and I will obtain that the derivative of a, which depends on q dot q with respect to q multiplied by q dot, so I differentiate this one, plus the derivative of a depending on q and q dot with respect to q dot multiplied by the derivative of q dot is q dot dot, and I'm happy here because I make a q dot dot appear, and it corresponds to the missing equation. So this one, I will recall that it corresponds to the derivative respect to t of a, which is dependent on q and q dot. Okay. So it means that now I have this equation. So I have 2 equations, and so the first one is d of dt of a of q dot equals 0. So it is a vector equation but corresponding to 2 scalar equations, and the Euler-Lagrange equation q dot dot minus tau of q and lambda equals 0. So now I have 7 equations, 7 variables, and all is linear in q dot dot and lambda. So this one and this one, okay, I will call it, so all this, I will call it for simplicity S, which depends on q dot lambda and q dot dot, and again I am linear with respect to lambda and q dot dot. So since I am linear, I see that S is equal, can be written into the form m of q dot multiplied by lambda q dot dot, due to the fact that I am linear in lambda and q dot, minus something, I will call it b, q dot. And if I do this, I can have an expression of m due to the linearity. I know that m is a mass matrix, and in fact it does not depend on q dot. I can observe it, but so this is why I will write it m of q. Okay. So m of q corresponds to the derivative of delta with respect to lambda and q dot dot, since I am linear, this one. Okay. And if I isolate in this equation b, I have also an expression for b. So I have a way to compute m and lambda by computing derivative. And if I do this, this equation, okay, that I have here, can be correspond to this. So to obtain this, I had to isolate in this equation this one. Oops, excuse me. I had to isolate this one, and I obtained here, so I had to inverse this matrix, and I obtain, once I have isolated, an expression where lambda 1, lambda 2 has been isolated, but also this corresponds to q dot dot. We can see here that the equations are quite horrible to obtain. This is why I need to use SIMP for that. To obtain this equation using SIMP, in fact what I want is only this one. We'll see for the state equation. The other one, I don't really need them. So to obtain this, I recall that I have already written this one corresponding to the building of Q. Then A of Q, I recall it was given here. I rewrite here. I build A of Q here. Then I recall that small a is defined by this. So it's A of Q times Q dot. It is one I get here. Then I compute the derivative. So I do not compute by hand. I use SIMP. This is given here. Okay. I define this vector. I define also some function for the Lagrangian parameters. And I recall that tau is given by the linear combination of the line vector for A. Okay, this one and this one. Okay, so I print it. The matrix S. The matrix S was given here, was defined here. So I write the following line. Then M, I rewrite M and B as be defined from S. So I can compute them by compute the derivative of S with respect to this one. It is what I do here, thanks to the Jacobian respect to the lambda and ddq. Then I will get this. And for B, I isolate in this equation this minus that to obtain B. It is what I get here. Okay. And then I will isolate this one thanks to this. So I invert this matrix in order to obtain this equation. But in fact, only these one are interesting for me. And if I do this, if I print them, then I will get this. Okay. So now I have my state equation for my will. So recall that the state variable were x equal to c1, c2, phi, theta, psi, and the derivative phi dot, theta dot, and psi dot. This why to obtain the state equation I should obtain something like x dot equal f of x. So the derivative of the state variable correspond to c dot 1, c dot 2, the derivative of the Euler angle and the second derivative. And here I only have expression with respect to c1, c2, phi, theta, and psi, and the derivative phi dot, theta dot, psi dot. So it means I have my state equation. This one corresponds to what has been obtained here. It is why it was important for me to have the second derivative of the Euler angle. This one is trivial. Okay. And this one has been obtained when I from the matrix A, okay, from the equation corresponding to the derivative of C1, C2 and expressed with respect to the derivative of the Euler angle. So now I have my state equation, and thanks to this I will be able to simulate my rolling wheel. If I want to combine with Python the symbolic computation made by SymP and the numerical computation, I need first to have a symbolic system, I call it SymBuild here, which build my with the Lagrangian and Q and so on, which will build my the expression for my the derivative of my state variable for the evolution function, and then I will lambdify, so create a Python function which tells me what are the state variable with the parameter, and which will return the evolution, so the derivative of the state variable. So lambdify will return a function. So this function, which corresponds to the evolution function of my dynamical system, is here. So SymBuild returns a function, a Python function. Then, of course, I will transform it so that it will better fit with what I will need after. So I will flatten, so my evolution function f, I will flatten the state vector x to build my state variable. Then I will call the symbolic function that has been lambdified, and then I will return my the derivative of my state variables. I will use this inside a Runge-Kutta integration chain for my simulation. Question number 6, I have to simulate the rolling list with some initial condition and to show that the behavior of the wheel looks similar to what we could expect, such as this picture. Okay, so first I have to explain the Python program I will use. I use the roblib library. Then I have my main function here, my main program, which simulates or rotate the rolling list. So I draw a 3D picture with a sampling time, and I have the main loop. And to start, I don't take the state equation I have obtained, but just I try to move one by one each of the state variable of the, so that I can see that the graphism corresponds to what is expected. So for this I will call the function draw given here, and this function draws the axis but also draws the wheel in 3D. So for this we have some change of frame, and I will call a procedure given in roblib just to draw in 3D the wheel, the shape of the wheel given here. Okay, so this is the program where I initialize the state as given here. I put my axis of the 3D frame here, and then I call the procedure simulator rolling list just to check all is okay. So first I just change the third state variable which corresponds to phi. Okay. I can see here indeed it rotates, but of course I can check one by one that all is okay. So for instance here it is a second angle theta, and I run it. Okay, we can see that it behaves as expected. The last layer angle corresponding to the heading looks okay also. Here I just change the center. Looks okay also, and so on. Now for the simulation, I will take the state equation I have already obtained in this exercise, and I will use for the integration scheme the classical Runge-Kutta of order 2 method. So it is implemented here. Okay. So in my program, I initialize the state vector as given here, and I call the procedure simmer rolling disk. I run the program, and at the beginning it has to compute the Lagrangian and the evolution function. And now we integrate, and we can see the wheel moving as expected. The energy remains constant, and we can see some precession effect. So it's not a perfect circular trajectory, but there is some oscillation corresponding to a precession effect. So we can see in the program that we call the function f. The function f is given here and uses the function f lambda that has been built by a symbolic computation, and the expression has been lambdified here. So this procedure, SimBuild, returns a lambdified function corresponding to a symbolic expression. For the last question, we have to find some initial condition so that the disk performs a perfect circular trajectory. So for this, I will start with the state equation we have already obtained, and we can understand that to have a perfect circular trajectory, we have theta should be equal to a constant. It means that theta dot should be equal to 0. It means that this is equal to 0, this is equal to 0, so all this is equal to 0. And we can understand that all this quantity should remain, so phi dot, theta dot, psi dot should be at least constant. So it means that all the second derivative should be equal to 0. So the first line does not bring us any new information. So since theta dot equal to 0, it means that this is equal to 0. So I remove this. And all the information is inside this equation. Okay. So for this, we can see that sine theta, this one is equal with so all this quantity is equal to psi dot square multiplied by sine theta multiplied by cos theta. So all this expression lead me, if I isolate this one, to psi dot is equal to 2 divided by 3r psi dot j tangent theta plus 5 divided by 6 psi dot sine theta. So it means that if I take for initial condition something such that this formula is satisfied, then I will perform a perfect circular trajectory. So let me check this. I take C1, C2 and so on as given here, but d phi is given by the formula I have just given previously. So if I do this, I start the simulation. First, we build symbolically the function after computing the Lagrangian and so on. And then we can see the wheel performing a perfect circular trajectory.